Welcome to the Deep Dive, where we tear through the research you shared with us and distill the most critical and often surprising insights. Today, we are strapping in for a high-stakes, low-level journey into a vulnerability that should feel ancient, yet remains terrifyingly effective: the buffer overflow.
It sounds old, doesn't it?
It does.
Yeah.
But when you look at the history of widespread internet worms, these massive data breaches, systems collapsing, the trail so often leads right back to this. It's a vulnerability that sounds simple on the surface, just a little programming mistake, but our deep dive into the source material immediately highlights its persistent danger.
Oh, the research is absolutely clear on this. Even today, buffer overflows are a perennial threat. They consistently feature on the Common Weakness Enumerations list, the CWE list, of the top 25 most dangerous software errors.
We're talking specifically about CWE 7A7.
Exactly. The out-of-bounds, right? It's essentially the modern name for this classic error.
And if you needed any definitive proof that this isn't just some, academic folklore, consider the most chilling nugget we extracted.
I think I know what you're going to say.
Studies show that most internet worms use buffer overflow vulnerabilities to propagate.
There it is. That connects this problem instantly to real-world chaos.
Yeah.
This isn't just a threat. It's the fundamental mechanism for global compromise in so many cases.
So our mission today is, well, it's threefold.
First, we need to unpack the core mechanism. What is an overflow, really?
Second, we have to grasp why it poses such a triple threat to security, hitting confidentiality, integrity, and availability all at once.
And finally, and this is the really fascinating part, we'll dive into the genuinely chaotic and frustrating complexity of memory management that attackers have to navigate to turn this simple coding error into a full system compromise.
It all starts with the foundational languages of the internet, doesn't it? C and C++ Act.
It does.
We noted a crucial point in the source material. Languages like C and C++ place an enormous amount of faith in the person writing the code.
A huge amount.
Yeah.
They fundamentally assume the programmer is responsible for data integrity.
There's no safety net baked into the language itself.
That's the core tension. C and C++ are valued precisely because they allow for high performance and direct memory manipulation. They don't implement automatic boundary checking on data structures like a lot of modern safer languages do.
And that lack of safety, that's a trade-off for speed.
It is, purely for speed.
Okay, so if I'm a C programmer and I ask the system for a small slice of memory, a buffer, to hold, say, 10 bytes of input, why doesn't the operating system or the compiler stop me if I try to stuff 50 bytes into that 10-byte space? What happens at that precise moment of failure?
Well, the system doesn't stop you because those safety checks were explicitly left out for performance. And that event, that's the buffer overrun or the buffer overflow.
So the data just spills.
It just spills. The excess data, those 40 extra bytes in your example, they just spill out of the allocated space. And here's where the problem starts. That excess data immediately begins overwriting adjacent parts of memory.
Stuff it's not supposed to touch.
Exactly. Data that belongs to other variables, or worse, crucial program instructions.
So at a minimum, the program just starts acting weirdly.
At a minimum, yeah. It behaves unpredictably. It might hang, or it might crash entirely. When a crash happens, because the program tried to access memory it shouldn't, we often see that classic signal, the seg fault.
And that crash itself, that already violates one of the pillars of security.
It does. But crashing the system is actually the attacker's least desirable outcome, right?
Oh, for sure. The true goal is to weaponize the flaw.
Absolutely. The goal is far more malicious than a simple denial of service. The attacker meticulously crafts the overflow data. They call it shellcode, so that when it spills out, it lands in a very specific, crucial memory location.
Like the stored return address on the stack.
Precisely. By overwriting that address with the location of their own malicious code, they can completely redirect the program's normal flow of execution.
And that's it. Game over.
They effectively seized administrative control of the system.
Which brings us directly to why this vulnerability is so dangerous. It doesn't just poke a hole in one area of security, it completely demolishes the three pillars of the CIA triad.
Confidentiality, integrity, and availability.
All three.
It's rare for a single vulnerability type to hit all three so cleanly. Let's break them down.
Okay, let's start with confidentiality. If the attacker overflows a buffer, they can often read the adjacent memory they weren't supposed to access.
Right. So imagine the buffer was used for something harmless, but sitting right next to it in memory is, I don't know, a session token.
An unencrypted password or some other sensitive user data. The overflow lets the attacker just read that information.
And then there's integrity. The attacker isn't just reading, they are writing.
This is the scary part.
It is. If they can manipulate that overflow to modify an arbitrary part of the data or the program itself, maybe changing an internal administrative flag from false to true,
Or modifying a critical config file.
they have corrupted the trustworthiness of the entire system. They're writing code where there should only be data, or changing good data into bad data.
And finally, as we touched on, if their exploit fails, or if their goal is just disruption, the resulting seg fault violates availability.
The service goes down, the user can no longer access it. Full house of failure.
So it's also important to understand where these buffers live, right?
Yes. While buffers can be overflown in the global stack and heap memory segments, the source material had a very specific warning that we should probably emphasize.
Which was?
Stack overflow can have the most significant consequences.
And that's because the stack is ground zero for managing the program's execution flow.
Exactly. It holds all the local variables and, crucially, those return addresses the program uses to figure out where to go next. That makes it the prime target for hijacking control.
Okay, let's connect this theoretical flaw to the real world. We often hear about modern operating systems and compilers being much safer. If this vulnerability has been known for decades, why is it still on the CWV Top 25 list?
Because the fight is a continuous arms race. You're absolutely right that modern systems have implemented numerous mitigations. We're talking about things like non-executable stacks.
Which stop attackers from just running their code from the stack.
Right. And, most importantly, address space layout randomization, or ASLR.
ASLR is an acronym people hear a lot, but for you listening, what exactly does it functionally do to stop these overflows?
It's conceptually pretty elegant. ASLR aims to defeat these exploits by injecting chaos. Every single time a program loads, ASLR moves the key memory locations, the stack, the heap, the libraries, to a random, unpredictable spot in memory.
So an attacker can't just guess that the return address they want to overwrite will be at address, 0xdeadbeef anymore.
Exactly, because that address will be different every single time the program runs.
That sounds like a pretty airtight defense. So why are we still having this conversation?
Because these protections, while they're excellent, they're not impenetrable. And sometimes they are intentionally lowered. The sources note that these protections can be disabled, maybe by a developer using a specific compile script like the compile.sh that was mentioned, to make debugging easier.
Right. If you're debugging, you want memory addresses to be consistent. It makes sense.
It does. But even when that protective layer is removed, the attacker still faces a pretty complex challenge because memory is still not static.
The shifting goalpost. Even when we turn off the randomization, programs and data still need to be loaded into RAM to execute.
Yeah, and that loading process is influenced by factors completely outside the code itself. This is the truly interesting part.
I mean, even with ASLR disabled, you can't guarantee the memory addresses will be the same.
Not at all. The sources list several factors that cause the program's memory location to shift around. We're talking about environment variables, the length of the program name, and arguments passed to the program.
So this forces the attacker to be incredibly precise. If their exploit is coded to hit address A, and some tiny external factor shifts the buffer to address B, the whole attack just fails.
It either detonates prematurely or fails silently. And this is where the source material provided some fantastic concrete examples.
Showing how external input just drastically affects the memory landscape.
Exactly. We can look at the contrast between two types of sample programs. One that takes command line arguments, and one that reads from standard input.
Let's start with the arguments.
Okay, so consider the first one, the sample program sorge.cpp. This program takes its input as an argument when you launch it. The research shows that the actual memory address of the target buffer shifts based on the length of that argument.
So if you run the program with a short argument, the buffer is at address X.
Right, but if you run it with a longer argument, the buffer gets shifted down the stack to address Y.
So the very data you are using to cause the overflow is simultaneously determining the location of the target you are trying to hit.
Exactly. It's a dynamic targeting problem. It makes a successful exploit incredibly unstable if the input length varies at all.
Okay, so now contrast that with the second example.
Right. The second example, so standio.cpp. This program prompts you interactively, reading data from standard input after the program has already started.
So it's already running and settled in memory.
Precisely.
Yeah.
And the sources confirm that the length of the data read from standard input doesn't shift the addresses of the buffer or other variables.
That gives you predictability. If an attacker can force the system to read the overflow data from standard input rather than a command line argument, they eliminate a major variable.
A huge variable. This distinction is absolutely critical for a reliable exploit.
It is. But here is perhaps the most counterintuitive and frankly kind of beautiful piece of low-level detail that we found.
The unexpected influence of the program's name itself.
It seems utterly illogical. How could renaming an executable file from, say, a .out to my test program, how could that change the memory layout? Why does the name length matter?
The why is elegant in its simplicity once you grasp how the stack is built. The name of the program, whatever you execute, is passed to the main function as the first element of the argument vector, argv0.
Ah, okay.
Since all those arguments are pushed onto the main stack when the program starts, the length of that first argument, the program name, physically shifts everything else that follows it on the stack.
Wow.
Think about it this way. If the default name out takes up 5 bytes, and you rename it to long exploitus program, which takes up 30 bytes.
You've just added 25 bytes of data to the stack before anything else even happens?
Before the attacker's target buffer even appears. So if the attacker had calculated the target buffer to be at address A based on a .out, renaming the file instantly throws their calculation off by 25 bytes.
Their whole payload will miss its mark.
Completely.
That is an absolute aha moment. Something as seemingly benign as renaming a file, something completely outside the programmer's control, fundamentally destabilizes the memory layout.
It really highlights the nice edge these systems operate on.
And the final piece of this memory puzzle, that involves the environment, right? We noted earlier that environment variables are also a factor.
A significant one.
Mm.
We're talking about the surrounding context. If you run a program under GDB, the GNU debugger, it sets environment variables like lines or columns.
And those also get loaded into the program's initial memory layout.
They do. They consume stack space and contribute to the overall instability.
So an advanced exploit developer has to account for this.
They do. They often intentionally manipulate the environment just to find a baseline. For example, they might use the invade command with the mi option.
Which does what?
It ignores the current environment and starts the program in a completely stripped, clean environment. It lets them eliminate variables that are constantly shifting, giving them a slightly more predictable memory map to work with.
But the fact they have to do that at all just shows the extreme level of precision required.
It really does.
So what does this all mean? We started with a conceptually simple coding error, forgetting to check input size, and we ended up in this highly technical struggle against unpredictable memory addresses, environment variables, even the length of a file name.
It means that while the flaw itself is old, exploiting it reliably in a modern context is a game of extreme precision and persistence. Buffer overflows represent a complex, triple-threat vulnerability to the CIA triad. We've established that the primary challenge for the attacker isn't the overflow itself, but accurately predicting or navigating this constantly shifting landscape of memory addresses that modern systems, even with protections off, still present.
So the next time you hear about a major security breach, a rapid-fire worm, or a crash that takes down a critical service, you should recognize the underlying tension here. It's this constant battle between the programmer's ultimate responsibility for data integrity, which C and C++ impose for the sake of speed, versus the inherent instability of the system, where a single character change in a file name can change everything.
Well said.
And that leads us to our final thought for you to chew on, based entirely on the fragility we've uncovered today. If the core programming languages that power the internet, C and C++ AB, place ultimate responsibility for safety on the programmer, and factors as simple as the program's name length or the content of the execution environment can cause critical memory locations to shift, how stable can any complex software system truly be?
It's a deep question. This ongoing reliance on manually policing memory boundaries is why many in the industry are now rapidly pivoting toward languages like Rust, which enforce memory safety by design.
So the question you should be asking yourself is performance truly worth the perennial risk that a simple typo could compromise the entire system?
Something to think about as you decide which technologies you trust.
We'll catch you on the next deep dive.